Hi there, in this video we're going to derive the complex version of the Fourier series. Now I've rewritten the Fourier series out here, and now we derived that in the previous video. It really tells us that we can approximate this function f of t using a series of cosines and sines which are integer multiples of a fundamental frequency omega naught. Now we know these values here, the cos, the cos and the sine, but we don't know what these scalar coefficients, the an, bn and a0 are that allow us to approximate this function. But we've seen in previous videos that we had a solution to this, because if we can think of these values of the cos and the sine as forming an orthonormal basis, then we can use the dot product in order to find these scalar coefficients. Now these are the dot products that ensure that these functions here, the cos and the sine, form an orthonormal basis. So when we apply the dot product to the function f of t, we take f of t and we dot product it, we do the dot product, and if we use the cos n omega t section, it will give us our ans, and the sin n omega naught t will give us our bn's, and we can see that the factors here at the beginning, the factor of 2, we have that there because we need to normalize the vector space. It's not normalized unless we add this factor in. Okay, and we've seen that anyway in the previous video when we derived it. Now what we want to do is take this Fourier series and simplify it so that we replace the cos and the sine with an e to the I n omega. Okay, and we also want to take the dot products here and we want to replace these cosines and the sines with an e to the I n omega. So we'll end up with one equation here for this and one equation here for these three here. Okay, now what we do is we use the two identities here, and again we've seen these in a previous video. So cos n omega t equals e to the I n omega t plus e to the minus I n omega t up in 2. You notice I've missed out the 0 and the omega 0. Now it's just understood. We know that's omega 0. It just saved me writing it in all the time. I just add it in at the end. Okay. And the other one is sin n omega t equals e to the I n omega t minus e to the minus I n omega t upon 2i. Now again we've seen those, so but we can quickly just go over it. Again a graphical representation. If we had a phasor that's rotating, okay, and we say that's the imaginary plane and that's the imaginary axis and the real axis, then we could say that the cos omega t, well the cos omega t, if we projected down this line here, that would be our cosine function. Okay, and we can write that as e to the I n omega t. So imagine a phasor here travelling in that direction, that's the e to the I n omega t, and another phasor here, e to the minus I n omega t, that's travelling in that direction. When we do the vector sum of these two phasors, it will land somewhere on that real line, and if you picked another point for these two phasors, they would be there and there, say for example, then again you would end up on that line. So it maps out the points on the real number line, and again it's divided by 2 because there's 2 of them, so you end up with twice the distance here and you need to half it to get back to the right value. Okay, the similar thing can be said about the sine omega, the sine value as well. If we were to do the projection onto that axis there, then we'll have our sine function, and our sine function we can written again e to the I n omega t, so we can think about a phasor like that, okay, say rotating in that direction, okay, and it's e to the minus I n omega t, which again is a phasor up there, right, but it's rotating in that direction, but it's the negative of that phasor, so it's equivalent to taking that phasor and putting it down onto that axis there. So again, when we add these two up vectorially, we get that point there and that point there. Okay, so it gets to a point on the imaginary axis, and if you were to take two different values of these, maybe say up there and there, when we add these vectorially, then we end up with a point on that axis. So it goes up and down that imaginary axis. And again, we've got to divide by 2. In this sense it's 2i because it's in the imaginary axis and we want it back to the real value. Okay, so that gives an indication of the graphical representation and what it is we're doing here whenever we add in these complex exponentials. So what we're going to do is we're just going to take initially this function here and we're going to replace the cos n omega t, the sin n omega t with what's in these identities. Okay, so I've just rewritten that out again. Now I decided just to write it out as opposed to me, writing it out as I'm doing it, because little errors tend to creep in. Okay, so I've just rewritten. I decided just to read over it. So we got g of t equals a0 plus the sum from n equals 1 to infinity of an. Now the cos n omega t is now replaced by this. Okay, and the bn and the sin n omega naught t is now replaced by this. Now what we'll do is just multiply these out, so you're going to get 1, 2, 3, 4 terms, and then what we're going to do once we've multiplied them out is we'll gather like terms of e to the I n omega t and like terms of e to the minus I n omega t. So that's what we've done here. We've multiplied that out, and this here has become an upon 2 e to the I n omega t plus an upon 2 e to the minus I n omega t plus bn upon 2i e to the I n omega t minus bn upon 2i e to the minus I n omega t. Now what we'll do then there is we'll take this I here, and when we can take the I up, we take the I up, it becomes minus, and again we take that I up there, that will become positive. Now we can do that because when we write 1 upon I is the same as saying minus I. Now we can see that there because if we were to say multiply these up, so that would be I times minus I, then that would have to be equal to 1. So that's the square root of minus 1 times the square root of minus 1, but it's the negative of all of that. Okay, well that's going to be equal, well the first two terms is going to give us minus 1 times minus will give us a value of 1. So this little identity holds, so that's what we've done here. Okay, and now what we'll do is we'll gather the like terms, so we'll gather terms of e to the I n omega t, so we'll gather this term here with this term here, and we'll gather the negative I n omega t term, so we'll gather this term here with this term here, and that's all we've done here. We've just gathered like terms. Okay, now this is still a summation from n equals 1 to infinity, but the next little thing what we'll do is we note that if you have e to the minus I n omega t, what we can do is we can change this to a plus I n omega t, and then we can change the summation from 1 to infinity to minus infinity to minus 1. Okay, now you can see that as well, because all you're really doing is this little identity here, which is let's say you have the sum from n equals 1 to infinity of a to the minus n. So let's say if a was a half, okay, then so you would have, for the first three terms, you would have a half to the power of 1, okay, and a half to the power of 2, and a half to the power of 3. Okay, in fact actually yeah, in this instance here you would have half to the power of 3, so you'd have 1 upon 2 plus 1 upon 4 plus 1 upon 9. Okay, now that would be the same as saying the sum from minus infinity to minus 1 of a to the n. Okay, so if you put some values in for that, you'll see that that indeed does work out like that. So now we have our two terms here. So what we can do is what I want to do is we want to put these together into just one series. So the series will run from minus infinity to plus infinity, and we take our value Cn, and it's e to the in omega t. Now we're just calling these Cn, okay? So now we've got a Cn plus, okay, which is the an minus ibn upon 2, okay? So the Cn plus, it's all the values of n when from 1 to infinity, and the Cn minus is all the values from minus infinity to minus 1. Now the value at 0 will be, well, e to the 0 by 1 will just be c0, and we can see that c0 from further down we'll see c0 is equal to a0. Now this here is the complex version of the Fourier series, the whole thing, okay? Now what we want to do is we want to see if we can find the complex version of these dot products here, okay? Now what we'll do is we'll just take we can pick a value of Cn, so we pick the value initially, we'll pick the value Cn plus, okay? So we're going to have Cn plus is an minus ibn upon 2. So if we come back up here, in order to get this an and bn, well, we know our an is written as this, we know our bn is written as this. So now what we want to do is we want to take our an minus ibn upon 2, and that's just what I've done here. So the an is going to be 2 upon t naught, the integral from 0 to t naught of f of t cos n omega t by dt, okay? So that's just a value for an, and it's all divided by 2. And we'll take bn, well the bn was 2 upon t naught, the integral from 0 to t naught of f of t sin n omega t by dt, and we're going to multiply it by our value of I, okay? Now whenever we take the factor of 2 away, so it's division by 2, 2's to cancel out, 2 cancel out, okay? The minus I, we can take the minus I inside here, okay? So it would be minus I sin n omega t. So we just end up with our Cn plus would be 1 upon t naught, integral from 0 to t naught f of t e to the minus j omega, and there's an n as well, omega nt by dt. Now that's us shown that it works for all the positive values, the Cn plus. Now what we could do is we can show that we get the same answer for all the values Cn minus. So that's all I've done here. Now Cn minus, the f of the cos n omega t has been replaced by the negative n omega t, okay, because it's negative values of n, and again there's negative values of n there, and we just use the trig identity. So cos of a negative value is the same as the cos of the positive value, so that's this line there is the same as this line here, and the sine of a negative value is the same as negative the sine of a value, okay? So this negative comes out, and that just changes there to sin n omega t. So that there is just the same as in the previous one that we looked at up here, exact same format. So divided by 2, and the 2's cancel out, so we end up with again 1 upon t naught, the integral from 0 to t f of t e to the minus jn omega t by dt. So that is the same, so Cn plus and Cn minus are the same, which is good. And also if we look at the C0, then the value there is going to just end up with e to the j omega t, so e to the power 0 is just 1, okay? So that would just be dotted with the 1, which is indeed just this dot product here, which gives us our value for a0, okay? I hope this is not a bit too dry. It's sounding a bit dry actually, but anyway I'll continue with it. So what we have then is a function here. We can approximate this function of time by a series of exponential functions, and the magnitude of the functions given by some value c to the n. Okay, and then we can then say, well, how do we find the values of Cn? Well, Cn could be found by again a dot product, and a dot product, and that's the dot product there. Okay, so it's again at 0 to say t0. Okay, now that then is our what we started off. We'd say we wanted to work out complex form of our Fourier series. So that's the complex form of the Fourier series, and then we wanted to find out how we can create the dot product to find the value Cn. Well, that's the dot product there to find the value Cn. Now you can think about these in the same way as we did in the Fourier series, that this here is a dot product, e to the in omega t. Now it's in omega naught t, so I'll put the naught in at the end, okay, because it's a multiple of fundamental frequency. Okay, so it's in omega naught t is the an orthonormal basis. Okay, the in omega naught t is an orthonormal basis, and it's defined as an orthonormal basis via this dot product here. Okay, so it's the same sort of thing. That's all for now. Really, I'll try and get on to the next video and get a few examples, and then after that we'll move on to the derivation of the Fourier transform. But remember, you don't have to remember all these things. It's the kind of thing that you see once and you think, okay, I've seen that, and you know where to go and get it if you're ever asked about it or you feel any need to look at it. But what matters is, what I think matters is that you comprehend that this is an approximation. This is a series that we're using in order to approximate this function, and this is our dot product that we use in order to find our value of our Cn. Okay, thanks for listening and goodbye.